So let me just first say that this is all a joint work with David Kazhdan. So I'm not going to write as nice as Adam. Nobody can compete with that. Anyway, right, so this work came out of an attempt to get a fresh look or try to understand better the inverse theorem for the Gowers norms over finite fields, for which we don't have a good proof at the moment. Or we have a proof, but it's maybe looking for a better understanding of it, and maybe try to understand this theorem in more algebraic terms. So this is what I want to talk about. But for this, here is a model question. Okay. So suppose you have a group G. G is a group. Abelian, say countable. And you have L is some vector space countable over some field F. Let me write K for. And you have a function rho from G to the endomorphism group of V. So these are all homomorphisms from V to itself. And you're given this algebraic data that for any two elements, G and H and G, if you look at rho of G plus H minus rho of G minus rho of H, then this operator has rank that is bounded by some universal number R, okay, some number R. Okay, so you're given that for any uniformly over the group G, for any two elements, you have an almost homomorphism. So if this were 0, this would be, if R would be 0, this would be a true homomorphism. So this is sort of an almost, in some terms, an almost homomorphism. And you want to ask the question, so the question is, can you find, does there exist a question mark, a homomorphism, an honest-to-God homomorphism, what homomorphism? Chi, such, I never remember how many M's, such that the rank rho is close to chi up to some bounded rank. Okay, so if I know that my function is an almost homomorphism in terms of rank, so the rank of rho of G plus H minus rho of G minus rho of H is smaller or equal than R, then can I find a homomorphism such that the rank of, such that the difference between rho and chi is of bounded rank? Okay, and depending, so this number, well, I would want it to, obviously I can have this infinite, so I want to find a finite R depending on R. Okay, so here's like a baby question you can think of. Here's an example. Suppose your group G is just Z, and you're looking at this question, so you have this rho from G to end KV, and suppose this R is 1. So suppose you know that rho of G plus H minus rho of G minus rho H, this rank of this thing is bounded by 1. Right? Suppose you know this, then it's not difficult to show. Then you can sort of follow this around, so you know that the kernel or the co-kernel is just a dimension 1. You can try to follow this around, and you can show that this R of R is smaller or equal than 2. So, but okay, so you can do this. You can play around with this question and try to show this. But already I have I don't know how to do this if R is equal to 2. Okay, so yeah. Okay, I will describe an instance in a minute where we can solve this. But But actually, I'll give you kind of a framework of, there's a big stack of lots of problems that come up from formulating these type of problems, and kind of very basic ones we know nothing about. So for example, this one I can't answer. Here is what we can prove. So here's the theorem. If G is a V, which is a vector space over, so infinite dimensional vector space over my field K, and K is a prime field, and of characteristic, well, we can do it for greater or equal than 5. Then the answer is yes. Then R of R is smaller than infinity. Or, yeah, so there is this function R, and of course you can also then ask questions whether how R depends on R, and I can't not going to be able to answer that. Yeah, but the point is that this is a purely algebraic question. So I just ask a question, and matrices or infinite dimensional matrices, and I know this rank is. I'm just giving this condition on the rank, and the only way I know how to prove this is using analytic means. So I'll describe to you a proof of this theorem using analytic methods. But before I do that, let me first describe a slightly more general theorem that we can prove. So here is a theorem, maybe some formulation before that. So yeah. So for D. No, if V is a vector space over K and K is a prime field. Okay, so it's an infinite direct sum of FP. Well, I was going to use L over here. You see, it doesn't matter, right? They're all the same. But since you mention it, then right. So for D greater or equal than 2, let us denote by, fix some D, fix D greater or equal than 2, and what was my notation? So let MD, these will be polynomials of degree D, homogeneous polynomial of degree D on this vector space. So you can think of these as polynomials. I have this infinite collection of variables, and I'm looking at polynomials in this collection of variables. So V, I think, V is my infinite dimensional vector space over my prime field K. And I'm looking at homogeneous polynomials. For any homogeneous polynomial, one can define the notion of rank in the following way that will kind of sit well with this notion here. So define if P is a polynomial. So if I have a polynomial here, then I can define the rank of P, P is of rank R, then. So this is not the theorem yet. This is just the preparation. So P is of rank R if I can write P as a sum of Li, Ri, I equals 1 to R, with Li, Ri, homogeneous polynomials of degree greater or equal than 1. Okay, so let me show you that you feel comfortable with this definition. If D were to equal 2, then this would be just quadratic polynomials, and then this would say that this would correspond to the regular definition of a rank of a quadratic polynomial as a sum of products of any quadratic polynomial, any matrix of rank R you can write as a sum of products of R linear. there is no, the d is the degree, I'm fixed, okay? So, yeah, right, but p's of degree d, now I'm writing, these are of degree strictly greater than 0, strictly greater than strictly greater than 1, okay? So if you think of this as a quadratic, you could write a quadratic, you know, the general inner product quadratic would give you something of ranks maybe n over 2 or n or something like this, of the same of if you're in n variables, okay? So you try to write your function, your polynomial in the most efficient way as products of lower polynomials, but I want it to be strictly greater than 0. So for d equals 1, this is empty, right? This just be constant. This would just p of degree, this would just be constant. Yeah, no, but I won't be able, yeah, okay. Sorry? Yeah, well, I could either say that or say rank small or equal than r, and then. Sorry? Okay, so great. Well, tell me later, and then excellent, okay. Maybe also there, well, I would be really, really happy if there's some other proof of this theorem that doesn't follow through the way I am. So if I'm going, so if there is, then that would be great. Anyway, so so I can define this notion of rank in this way, and again, okay, so now, so now I can say the same thing. So the theorem would be that if I have a map, a map rho from V to MD, then such that for any gene H, rho of G plus H minus rho of G minus rho of H. This rank of this is bounded by R, then I can find a homomorphism, then there exists a homomorphism chi from V to MD, homomorphism such that, same as before, such that the rank of rho G minus chi G is smaller or equal than RR. There exists a homomorphism chi and an R of R such that this happens. Okay. Okay. So.
I have a question about the first theorem. Before you go on, what G are allowed in the first theorem?
This one. Yeah. This is G is V is a vector space over infinite dimensional vector space over a finite field over the prime field K.
Okay, so the group here is the same as the vector space.
Yeah. Well, you can call them V and L if you want, okay, but that won't really make a difference. Okay. Okay? Yeah.
Are we over an again, and V here is the vectors over
yeah.
infinite dimensional vectors?
Yeah. Yeah. So V is that one. And this is the context. Yeah, okay. Yeah, okay, I confused you. The same V in both places. So thanks for that. Okay? But, okay, you can think of these, you don't really, over here you can think of these as polynomials over FP with variables x1, xi, and just, call this V, but, okay? Right, so before I describe how to go about to prove this, I want to reformulate this or introduce this notion of approximate cohomology. It's approximate with two P's. Cohomology, just kind of an algebraic cousin of various other notions of bounded cohomology or epsilon representations and stuff like that. But this is an algebraic notion, and this can describe this theorem as a calculation in this world. So suppose you have, suppose M will be an abelian group with the filtration. So I have the sequence of group Mi, which are rising up to M, and they satisfy these not sequence of sets, so Mi are subsets, so not groups. Mi are subsets that are going up to M, and they satisfy this condition that Mi plus Mj is in MCij. There is some constant Cij such that if I look at Mi plus Mj, then I don't run away. Okay? Melanie, are you happy? You like kind of no? Okay. Okay. So I have this collection of sets. So in our case, this would be this M would be MD. So these would be the D polynomials, and I would be taking this filtration by rank. Okay. Okay. So I have this. Right. So I can define what is and I have a G action. So I have G acting on M. G is some abelian group. Okay, so that will be our G over there, and we will be looking at the trivial action. But the general question would be for any G action, and you can define this notion of so what would be an approximate cocycle. So we say that rho is an approximate cocycle if the boundary map, if the image of, I'll write this in for our case in a minute, but if the image of the boundary map is inside Mi for some I, okay, I'll say that rho is an approximate cocycle. Well, if it were a true cocycle, then the image of the boundary map would be 0. So it would be an approximate cocycle if the image of the boundary map is in one of these filtered groups. So this would mean, in our case, let me just say, so in our case, or for n equals 1, an approximate, maybe I should say that. An approximate n cocycle if, if n equals 1, then d rho is just a function on two variables, gh. This will be equal, this is just rho of g plus rho of h, or plus the g acting on rho of h minus rho of g plus h. And if we take the trivial action, then this would just be, to say that this is 0, this is just a homomorphism. Okay, so I'm just putting this in place with a question I asked before. Okay, so this is a trivial action and a true homomorphism, a true cocycle, not an approximate one, is just a homomorphism. Okay? And similarly, say that, so maybe we should say this. Rho is a function from Gn to M. So we say that rho, which is a function from Gn to M, is n coboundary, n approximate coboundary if there exists some cochain T from Gn minus 1 to M such that the image of rho minus delta T is inside Mi for some I. Okay, so if this were equal to 0, this would be a true coboundary. To say that rho is a coboundary is to say that it's the boundary of some other map, and this would be an approximate coboundary if I allow this to be in one of my filtration groups. So in the case n equals 1, then if n equals 1, then n minus 1 is 0, then these are just constant maps, and the boundary of a constant map is nothing. So this, or 0. So this would just say, in the case of n equals 1, which is our case, this would just say that the image of rho is inside mi, which would just say in our case that this is a bounded rank. In my filtration, which is the filtration coming from rank on polynomials, this would just say that an approximate coboundary is an approximate coboundary would be a function whose image is bounded rank on this mi. Okay? Is the sort of the relation between this and this clear? I think this is a good formulation because then there's so many questions you can ask, and I can only answer one in a very special case. So now, okay, so you have so it's easy to see that these guys are that cocycles, that approximate cocycles and approximate coboundaries are groups. Okay, this is because of the filtration condition that mi plus mj is an mi plus j, or it's constant times m plus j. So you can define this. So the group of these, the group of approximate cocycles, this would be, we'll denote it by zn, zn tilde of gm, and this would be a group of approximate coboundaries. This would be bn gm, and there's a very natural map from, there's a natural map, there exists a map A from the regular cohomology GM. If something is a true cocycle or a true coboundary, then it's also an approximate cocycle and an approximate coboundary. So I have this natural map from Hn to Hn tilde m, which is Zn tilde mod Bn tilde. And the statement of this theorem, our theorem is that A is onto under the conditions I said before. So I'm looking just at the trivial action. But you can ask this question. Well, I don't know how to answer almost any other question about this. You can ask the questions, what about, maybe I should say AN. So A1 is onto. That's the only one I can say. But what about A2? Or any other questions? I'm at this moment unable to say anything about these. Okay, yeah, unless there is some hidden concept somewhere that I don't know, and somebody, I couldn't find anything about this thing in the. So there's lots of things in the literature about various things in a bounded cohomology, but I didn't see anything in this of this type. But let me describe to you. Okay, so I'm back to my original question. This is just a formulation. I'm giving you lots of questions. Anything you want to ask here, I think is not known. There are lots of things you want to ask. You might want to understand, but I'm back to this very basic question. This is kind of a matrix question, right? I have this map into this matrix group. I know that it satisfies this condition of almost homomorphism, and I ask, is it close to in this sense, close in this rank sense to a true homomorphism? And the way I want to describe to you how to prove that. So is the question clear? And that
theorem is for every
no, A is on. Of course not. But for G is this V, infinite dimensional vector space over P, a prime field. Prime, and actually, and this filtration, MD, so okay, maybe I should state it correctly now. Let me state I forgot all kinds of things I should say. Thank you, thank you for asking. So MD is comes with this rank filtration, and then I can show that A1 is onto, sorry? Yeah, homogeneous polynomials. And I can show that A is onto in the case where the P is greater than the degree minus 1. Thanks. Actually, very, very thanks. So I can't, this is there is some additional condition here. No, okay, there's this extra condition. A1 from, so any, yeah, A1. Well, actually, we can also calculate the kernel of this map, but I don't want to get into that now.
That's a nice question.
Yeah.
Does hn tilde differ from, suppose we just took a direct limit over h, the usual hn of g, comma, m mod mn, or m mod mi, let's say. How does this hn tilde differ from that?
So you should ask me that later, and I have to think about it. It will take me some time to reformulate that in terms I feel comfortable with, and then I'm happy to try to answer. Okay? But it's not at all clear. Well, I don't, if this group G is Z, I don't even, well, okay. You asked something about this thing over here. Okay, tell me later, and I'm happy to understand. Okay, but basically what I want to do is describe how to prove this. So how do you prove it? So the ingredients for proof. First ingredient is well, I told you I only know how to solve this group in algebraic means if I sort of in the rank 1 case. Like if I think, then I can sort of run around, sort of follow the transformation around. But in higher rank and for matrices, higher rank, I don't know how to do this. So there's a nice interpretation of rank, or a way to see rank in an analytic way. So this comes through, I'll call this bias implies low rank. So this is the first ingredient. And so I guess this is a theorem of Green and Tau. And in the high characteristic case, and Lovett, Kaufman in characteristic 2, and also for not exactly this what I want, but maybe in the formulation that I need, it's actually Lovett and some guy. I want to spell his name correctly. B-H. Homic. And it says the following. So I'm going to fix my field K. It's going to be some FP. Okay, so this is my prime field. And if the exponential sum, so I look at, so say, so I'm going to fix K to be FP, and now I want to think of V as a finite dimensional. So this is my group G. Okay, this would be a finite dimensional vector space. G, my group G, and my V that's actually in both places. So everything is V, and V is a finite dimensional vector space over FP. But I want to think of a very high dimension. So later I just piece the solutions that I get in each dimension to a very high dimension. And this theorem says that in this context, if you look at the exponential sum, e to the px, you average over x in V, so fix a polynomial. Okay, so p is a fixed polynomial. And this e over here would be e of t is e to the 2 pi I t over p. If I look at this exponential sum, then if this is biased, if this is greater or equal than 1 over p to the s, then p is of rank that is smaller or equal than some constant depending on d and s. Okay, so if I have this polynomial p, if this is a quadratic polynomial, then you know, right? If this is a quadratic polynomial, then if the exponential sum here, this would be something like 1 over p to the rank of your, yeah.
What are D and S?
If I know, if the bias of this exponential sum is greater than 1 over p to the s, then P is of rank that depends. So D is fixed. I can think of D as fixed for the, I just wrote here that this D over here to say that these results over here were dependent on P, and this result over here is independent of P. So this is maybe the state of the art, I think. Okay, is it clear what the parameter is? So D is this one is fixed in advance. I'm living in MD. MD for me is the all polynomials of degree D. The rank is expressing polynomials of degree D in terms of sums of kind of products of lower degree polynomials. Okay?
It's a little bit like the sort of results of Davenport and Lewis, where they take any polynomial and basically if this rank is large enough, or this H invariant is large enough, then you get cancellation in this exponential sum.
Okay, perfect. Well, this is the one I know, but okay. So maybe it's known in. Okay, I'm happy for any information. This is maybe 10 years old or something. So, or I don't know about the various improvements, but basically it tells you, okay, so if you have bias, then you have low rank or whatever H something invariant. So this is the one ingredient. The second one is that actually there is a kind of a converse. So the second one is that if P is of rank smaller or equal than R, or say rank R, I can look at, and it's of degree D, so I can look at these derivatives, delta D1 through delta H1 through delta HD of P. This would be delta H of P at the point X would be P of X plus H minus P of X. So this would be a multilinear. This would be multilinear in H1 through HD. Okay, so P was a homogeneous polynomial in D variables, and a homogeneous polynomial degree D, and if I differentiated D times, I get something which is multilinear in H1 through HD. And this is a, if P is of rank R, then this exponential sum, so maybe this is easy. This is kind of a lemma, small lemma. So this I don't know if has another, this is not so easy, but this is very easy. At least the proof I know that they have for this is not easy. Of e to the delta H1 through delta HD of P, if I average this, then this is biased by some constant depending on R. So if there's bias, then that implies low rank. In the other direction, if there is low rank, then not necessarily bias of polynomial P, but its multilinear version is biased, and actually without an absolute value, and that's kind of crucial. So this is, but this is very easy to show. But the third one, which is not, this is kind of the ingredient. This is what motivated me to think about this is the inverse theorem for the Gowers norms. Over finite fields. So this is a result by Bergelson, Tao, and myself, and other work of Tao and myself for actually the first time I was here at MSRI. We were working on this, and it says the following. So these results are about polynomials of degree D. So if a polynomial of degree D, it's biased, has low rank, and if it's low rank, then its derivative is biased. This is a result about a general function. Give me any function f. If f is any function from V to say fp, say to my field, and suppose I know that if I take this multilinear derivative, so if I differentiate it d times the same way I did over here. Okay, so I take, but this is a general function. It's no longer a polynomial. I know nothing about it. Okay, this is just some any function f. If I take if I differentiate it d times, and well, let me differentiate this e to the f of x d times. So I differentiate in the exponent. Okay, so this. Yeah. This thing, if this thing is, hope I did this, right? Yeah. If I differentiate this and I average over x and h1 up to hd, then if this thing is biased, if this thing is greater than some delta, then, well, I can't say that f is low rank or anything. It's not a polynomial of bounded degree, so it's just some function. But if the derivative is biased, if its d-folded derivative is biased, then my function f correlates with a true degree d polynomial. Then f correlates with a polynomial, with, maybe I should write it precisely, f correlates with a function q, maybe e to the f, correlates with a function q that satisfies that delta h1 through delta hd of q is nil. Let me explain this. What correlates mean and what is so this means that there exists some constant depending on delta, maybe C tilde, such that if I look at the average over f of, not f of x, e of f of x, q of x, damn it, bad. Okay, so let me, okay. Let me say that this is, okay, let me change it, and then in high characteristic, this would be true. This thing, maybe, yeah, okay, let me not do that. Yeah, okay, I'm sorry. Yeah, sorry. I hope I'm saying this. I hope I'm doing this right. I have to think about it in a minute. But then there is a function q whose d-fold derivative is 1. So if I differentiate d times, I get 1. If the characteristic is higher than this d over here, then this is the same as a regular polynomial that we are used to. But otherwise, there are some other things that come up. So if p is greater than d, then just a polynomial. Q is just a polynomial. Okay, so correlates mean that there exists something like this, where this is greater than c. Okay, in particular, what does this type of thing mean? Well, this is kind of, if I have any function f, okay? So I start out with a general function f. If I know that its d-fold derivative is biased, if I started with a polynomial of degree d, and its d-fold derivative is biased, then it's low rank, okay? If I start out with any function p, and I know that its d-derivative d-folded derivative is biased, then I know that this exponential sum is, then there is some function, some true polynomial q where my function f correlates with q. Okay, and this was the motivation for it. I was trying to figure out a different proof for this thing over here. This is the question that interests me. And actually, if you can solve this other question by some other means, then that would give a new proof for this theorem. So currently, the proof of this thing goes through ergodic theory. There is a translation for to an ergodic theoretic question. There is a structure theorem in ergodic theory, and then pulling back the result to this finitary context. And yeah, you were asking.
V is here a finite dimensional vector space?
Yeah, I said everything is going to be finite, and then later you can piece it all together to kind of a solution to the infinite dimension one. But you want to think of the whole thing as all these bounds. So V is finite dimensional, but all these bounds are independent of the dimension. Okay, so you think of the dimension as being, maybe I should have mentioned that. You think of the dimension as being large, very large, and all the bounds are independent of the dimension. Okay, so let me describe how to piece together these things. Actually, the idea is based on this idea of Green and Tao and independently Shacharlovich, who were trying to show this equivalence between conjectures, the polynomial Ruja conjecture, if whoever knows this, and some conjectures in additive combinatorics. And so it's related to ideas based on an idea from there. And what you want to look at is, so look at the function. So I'm reminding you where I am. I'm giving this function rho from V to polynomials to this MD. So this would be polynomials of degree D. And I know that rho of G, for any G, rho of G is a polynomial of degree D. And I know that rho of G plus H minus rho G minus rho H, the rank of this guy is bounded by some uniform R. Okay, so again, I'm doing everything in the finite context, but you can think of all of my bounds are independent of dimension. Okay, so V is finite, so I can make these averages and whatever, but all the bounds that come up are always independent of the dimension of the vector space. So I have this. I have this condition. So look at the function. Look at the function f of G. Let me write it H1 through HD. So which is equal to rho G of H1 through HD tilde, and this guy over where this guy, so if I have a polynomial P, I will denote by P tilde, this would be the multilinear version. So this would be delta H1 through delta HD of P. Okay, so I only have this, I need to go both ways. I need bias implies low rank and low rank implies bias, and I only know low rank implies bias for this multilinear version. So I'm going to work with the multilinear version of my polynomial. So I take my polynomial P and I look at its multilinear version, which is this guy over here, and I look at this function. This is a function on V times V to the D plus 1. Okay? And I can use, look, this condition looks very much like a derivative. If you apply this thing kind of twice, then this thing is going to look like differentiating, like differentiating twice. So show that delta H1, not H1, delta G1 R1 up to delta GD plus 2. RD plus 2. I'll write it in a minute. I take this function. I differentiate it. Well, for every fixed G, if I differentiate this function, this is a multilinear function of degree D. If I differentiate it D plus 1 times, it's going to die. Okay? Right? But my problem is how to relate it to this parameter G, which I know nothing about. Okay? For every fixed G, this is a nice polynomial, but I'm trying to kind of deduce from this thing a kind of a type of a linear behavior in this G. This would be a kind of a homomorphism. So I look at this, I take this function, I need to differentiate it sufficiently many times. So I differentiate it with respect to both parameters. Turns out that you should do D plus 2 times. So this thing, E of F, this thing, which is the same as looking at the U D plus 2 Gowers norm of the function, of this function with respect on the group V to the D plus 1. So you look at this thing, you use the fact that multilinear guys are biased to show that this thing is bounded away from 0. Okay? So you use this information and this information. Bounded rank implies bias to produce a function with a large UD plus 2 norm. Then you use the inverse theorem for the Gowers norm. So this is the first step. Second step is you use the inverse theorem for the Gowers norms. Would be use inverse theorem for the Gowers norms to conclude that this function f that I wrote before, that this function f, that f correlates with a polynomial, but this polynomial is in all the variables h1 through hd. It's a polynomial in d plus 1 variables. Okay, so it's a polynomial on v to the d plus 1. Okay, this is my new space, but you can use this then 3. From this information, you can deduce that since you already know linear, so you know that for any fixed g, you already know linear behavior. You have some information on this function f. You know that this function f, when you fix g, it's a polynomial. It's this g, the only linearity you need to get is on this g. So you can use this to show that, to get a polynomial, this polynomial q, get this polynomial q such that, get that f of g, or not f, this original rho of g minus p of g, the rank of this is bounded for many g, for positive density g, number of g, and then propagate. And then 4 is use some basic facts in additive combinatorics to propagate. So propagate using approximate cocycle condition to all of g. Oh, v, g, v. Okay. Yeah. Okay. So, right. So let me sort of recap what was interesting for me and what I was trying to do. So what was interesting to me is this question over here, or a general question in polynomials. I have this polynomial. I have polynomials of degree d over a finite field, and they're over vectors for a vector space and over a finite field, and they are filtered by rank. So I have this I'm fixing the degree of the polynomials, and I'm interested in this rank filtration, and I'm giving some function into these polynomials, this group of polynomials that I know that is an almost homomorphism, an approximate homomorphism in terms of rank. I know that the rank is the homomorphism condition is satisfied for all pairs up to some given bounded rank. Okay, and I'm trying to find a homomorphism, and I'm trying to show that my function is up to bounded rank, a true homomorphism. Okay, and the way I know how to do this, well, I don't know how to do this in any algebraic way, and I would really like to see some algebraic proof of this. If one can come up with an algebraic proof of this, then that would give a new proof for this thing. Yeah, so the means to get is using these 3 ingredients. One of them, the first one is that there is a way to see rank. Okay, so this h constant or whatever, but there is a way to see, to view rank in an analytic way. And once you do that, then you can invoke this inverse theorem for the Gowers norms to get correlation with some polynomial and sort of use the cocycle condition to kind of get approximate cocycle condition to get kind of a homomorphism on to show that you're close to a homomorphism all throughout. Yeah, okay. I think I'll stop because, yeah.
So when you say rank for the ingredient 1 for the proof, is it the same rank as the rank that you...
Yeah, for quadratics. So you can think of a kind of, in the quadratic case, this would be the rank of the matrix. You can describe a quadratic function using the matrix, and it would be the same definition as what you think of as.
No, I just thought that they defined the rank in that paper slightly differently in the Greentown paper.
Right, they do, but then that's why I put this one in. Because they define it as some function, and then you can show that this function you can actually...
So can you use that definition instead of that one? Or?
I think this is a more, this different, maybe, but the other one is more, I find more natural in algebraic terms. So this one, in this paper over here, it's like a function of, but I find that this definition is more natural in algebraically natural, so, but.
Many questions. I'll also talk to you later. One of the questions is, so the H invariant or rank comes up in the circle method when you try to bound the singularities, and there's various conflicting notions of how to measure how singular a polynomial is. So I was wondering, do you get any result if you, instead of discussing the rank, look at the algebraic, well, at the singular locus from algebraic geometry?
Maybe. I don't know. You have to explain the question to me in more detail, and then I can try to understand.
Yeah, well,
But maybe not. Yeah.
Small rank would correspond to a large singular locus, a very singular polynomial, and small.
Well, you could try to do maybe something like that. I'm saying this is like a like it's one result, and I think there are like lots of other ones that are waiting for somebody to.
So this inverse theorem, I mean, one's normally, in a kind of integer setting, you see this appearing with nil sequences on normal.
Right.
Does everything just collapse to polynomials?
Yeah. Yeah, so bracket polynomials in this case are bracket linear is truly linear in this context. So.
So is there any quantitative results on R of R?
No, because the inverse theorem. So, well, the inverse theorem doesn't come with any quantitative data. So if you could do that, I think this part does. This part is quite quantitative. And the part that would kind of give you problems is this one.
But even if your whole formulation is not really in the morphisms, it's equally non-quantitative result.
Yeah, right, exactly. That's why I would like to see a different proof for this coming from some other thing. Maybe that would reflect on that. But yes, it's true. I can only, yeah. So yes, my question is yes, even though, yeah.
Any more questions? Yep.
Well, maybe this is, I'm just trying to understand your statement that you don't get these things being polynomials when the characteristic of the field
Yeah.
is small, because I thought if you have a finite dimensional vector space,
If,
that everything is polynomial.
it's just that if you try to classify the function satisfying this condition, that if you try to, maybe it's written, if you try to understand functions that satisfy this, they just don't take values in the field. So if you try to understand functions satisfying this condition, you'd need some, if the characteristic is lower than the degree, then you would have some functions of this. They look like polynomials, but they don't take values they're not polynomials taking values in the field. Okay, you'd need some, we call them non-classical polynomials, but maybe they have a different name in some H something, whatever, or somewhere else. But yeah.